The question that I have is, could you do an example on consolidation settlement of a footing? Let's do one more example here. We have a rectangular footing and the footing is uniformly loaded. Footing pressure is 200 kilopascal. The dimensions of the footing are shown here, 10 meter by 15 meters. This is the plan view. We have a clay layer sandwiched between an impermeable layer and a sand layer. Water table is right here. The densities and other relevant properties of the two layers are given. In this problem, we are interested in the differential settlement between points A and B 2 years after the application of the load. So what's the approach? Well, we want to first calculate the ultimate settlements at points A and B, and then we want to calculate the average degree of consolidation at these points. From that, we want to calculate the settlements 2 years after at the 2 points, subtract one from the other to calculate the differential settlement. Let's first go ahead and calculate the initial vertical stresses at points A and B. Since both points are at the same depth, initial stresses at these 2 points will be equal to each other. I calculate a value of 191.9 kilopascal for the initial vertical stress at both points A and B. Basically, you calculate the total stress, pour water pressure, subtract one from the other in order to get the vertical effective stress. Now let's go ahead and calculate the vertical stress increase at point A. Remember the chart we have for rectangular footing gives you the vertical stress increase below a corner, right? So I'm going to take this and divide this into 4 equal parts such that point A is at the corner of each of the 4 sub-rectangles. So if I calculate the stress increase due to one of them, all I have to do is to multiply that by 4 in order to get the total change. So I calculate my little m, little n, and go to this chart and pick up the value of the influence value. I'll let you look at the chart from your book. But just to show you where the point plots, my point plots around here. So that gives me a value of 0.06 for the influence value. Because the pre-consolidation pressure is very large, both the initial point and the final point plot on the swelling line. All right, so the value of the vertical stress at this point is 192. Value of the vertical stress at this point is 240, which is 192 plus 48, right? And so now we apply the equation for calculating S infinity, which is delta E, which is given by this equation, multiplied by H divided by 1 plus E naught. And I get a value of 4.8 centimeters. Then I calculate my time factor. The time factor works out to be 0.0125. I want to call your attention here to the value that I used for H. Now this is a singly drained field layer, right? And therefore you need to use the entire layer thickness for H. So I'm using 20 meters over here. Anyway, so since the time factor turns out to be reasonably small, I took a chance and applied the simplified equation I talked about before. So this simplified equation is valid only if U average is less than 60%, right? But I don't know that until I calculate that. But it turns out that U average is only 12.6%, and therefore this simplified equation is valid. Now I can calculate my settlement at point A 2 years after the application of the load by this equation right here, and it works out to be 0.6 centimeters. So we need to now repeat this for point B. So here are my calculations for point B. You can follow this pretty easily, but briefly, point B happens to be a corner of the rectangle, right? So I calculate my M for the whole rectangle, 10 over 15 and 15 over 15. for little n, and then I go back to this chart again. I get a value of roughly 0.152, and that gives me a change in vertical stress at point B of 200 times 0.152, which is 30.4 kilopascal. As before, because the pre-consolidation pressure is very large, both points 1 and 2, the initial point and the final point, plot on the swelling line. So now I apply this equation and I get a value of 3.2 centimeters for S infinity, and U average is the same as before, and therefore the settlement at point B 2 years after the application of the loading works out to be 0.4 centimeters. Now we can calculate the differential settlement between the 2 points. So the differential settlement is only 0.2 centimeters at this point.